Today we are going to continue our discussion on Unit 1, Matter and Measurement, where it's really mainly focusing on the matter part of it still, because, well, that's what we go with. Just as a nice review from the last time, macroscopic, we can see. It's the thing that we can see easily with our eyes. Those items. When we go into the lab, we see things that are macroscopic. But what's happening in chemistry is happening at the particulate level. It's happening at the particulate level a billion times over. So we need to understand what we're seeing is happening a lot for us to be allowed to see it. Because otherwise, we wouldn't be able to see it. And so it does allow for that. Now, the microscopic doesn't really happen all that much in chemistry. That's more of a biology thing. And they have their parts and they utilize those and they feel important with those. But we kind of do. And then why sometimes people like physics more than chemistry? Because physics deals with the macroscopic almost solely. And it almost deals with the macroscopic to a level that is way larger than our understanding can hold. Okay? And so that's, sometimes why I always say I teach the hard sciences. Okay? They're not the squishy ones. Squishy ones are the biology because they squish when you touch it. Chemistry is hard because you're dealing with things that you can't really see. Physics is hard because it's dealing with things that are so large in scale that it's hard to comprehend sometimes. They're not hard, but that's what it becomes. So it's these different sizes, and you'll find that I like to talk about three things as we go, and especially today when we're going to talk about some other part. As I mentioned before, laboratories, macroscopic. But what's happening is happening at the particulate level. In physics, like I said, even then, but the physics, what's nice about physics is the macroscopic stuff that we do in the classroom in physics can be expanded, that understanding can be expanded out. In chemistry, we had to come up with new physics to explain what's happening at the particulate level. And it became quite the debate, and that really comes into Unit 2 when we talk about the atom, the kind of the beginnings of the atom. Okay? Because that's where it lies, at the particulate level. And even the atom itself. We know, most of us understand, or at least could rattle off the big, so to speak, and I'll put that in quotations, the big three of the subatomic particles. What makes up the atom? Right? Most of us would be able to rattle off those subatomic particles. And we will make that connection between the lab and the other as we kind of go through there, as we will do our next kind of lab in a way. So, how do we show this off? How do we show what's happening at the particulate level if we can't see it? It's really hard to envision things if we can't see it. Well, the first thing that a lot of us would understand would be chemical formulas. The chemical formula helps us. We're being asked to memorize the symbol and the name for the chemical formulas, for the elements on the periodic table. Most of us probably could have looked at that before last Friday and saw that the C is for carbon. Sorry, Cookie Monster. And the H is for hydrogen. But what does those 2s and 6 represent? It represents how many of each atom that are present. There are 2 carbon. There are 6 hydrogen. Now that doesn't tell us anything about how they're put together. That's where the models come in. And these are just a couple of the models. We even have structural models of the atom that tell us even more. And structural models of the atom are pretty easy to put together because all we do is use the symbols that we have to represent the location of those atoms. It looks a lot like the ball and stick model. But it really doesn't look anything like the space filling model. All of those are just different ways of representing the same compound. We call this compound ethane. That's not important at this time, but it is just so it's there. Okay? So we have a lot of different ways to represent some of this stuff. And that sometimes becomes problematic. And I could even if I took more time, I probably could have drawn the structural formula, which looks like the ball and stick, to look more like the ball and stick model. To have the hydrogen kind of off at an angle, as they probably should be. But most chemists would be able to look at my drawing and go, oh, that's ethane. Okay, yep. It's just not drawn structurally sound. Okay? You're drawing blueprints, you want to make sure they're a little bit more structurally sound. You don't want to have, wavy things inside those blueprints. But regardless of what model we choose, they all have their place. So that's when, as we move forward, we'll use these different models. And just like in the subatomic particles, I really only like to focus on the 3 model, or the 3 things of although that didn't. The 3 main states of matter. Just like the atom, 3 subatomic particles, 3 states of matter. Is there a 4th? Yes. Most of us know of it as plasma. Is there even more than that? Yes. But again, why worry about Bose-Einstein condensates if we don't really truly understand what's happening at the particulate level of solid, liquids, and gases? And I think that's the difference that we get to. Is many of us would know solid, liquids, gases, plasma, and be like, okay, solids are just hard. Liquids are, well, they're liquid. Most people would call liquid, they'd be like, oh yeah, liquids are, water. It's like, well, water can be a solid too, just depends on the temperature and the pressure. And gas, well, that's like air. Well, now you're starting to look like almost alchemy, elemental talk, where you're just kind of breaking them down to their simplistic states of matter. But air that we breathe is much more complicated than it's just air. 78% of it is nitrogen, an inert gas to us. 21% is oxygen. That doesn't leave very much, does it? You're like, wait a second, you're at 99%. 0.9% is argon, a noble gas. The remaining gas is less than 0.1% added all together. And they're like, so yes, there's a lot of stuff left. And it makes up a very small amount. There are some big ideas that we need to understand with a solid. It has a fixed shape and definite volume. And I'm going to resize it so I can even do maybe a little Venn diagram here for us. Okay. So we have a solid, fixed shape, definite volume. Where we have a fixed shape. Definite volume. And it's not compressible. You can't take a metal and compress it. It just flattens out. Right? You're not actually compressing it. A liquid is a material that has a definite volume but not a fixed shape. Because a liquid can change, and or sometimes we say takes the shape of its container. And you're like, whoa, that's some different thinking. So, liquids have a definite volume, but no shape. Because if you took a glass of water at home and you put it in a mug, a coffee mug, which has a different shape usually, the volume doesn't change. The amount of water does not change, but what changes is where it looks. Now, say if you have a vase or a vase, if you want to be fancy, okay? Or a wine goblet, or a champagne glass, different shapes, and you pour that water inside them. The volume doesn't change, the shape that it is changes. So they don't have a definite shape. So the shape is there. A gas does not have either. It has no shape. And no definite volume. Because the only way to define how big a gas is, you have to seal it. You have to lay it down and say, okay, now we have this. Okay? And so if I take, I'm going to draw here and see if I can get this on here. I'm going to take, and again, when I'm drawing, just understand that my best drawing skills came from my 7th grade art teacher. I never took an art class after that. Okay? That'll erase that a little bit. So I got my little Erlenmeyer flask here, right? If I take and put a top on my Erlenmeyer flask, I now have defined the container. I now can say, hey, if I had a gas inside that Erlenmeyer flask, which if I just have it open to the world before, it would be just that. Therefore, the volume would be not definite. But now that I put a top on it, now it's definite. Maybe it's a stopper and it sticks inside a little bit. Okay? And so we now go, okay, how much gas have I trapped inside that Erlenmeyer flask? And we're like, well, I don't know. How do we measure something that we can't see? We use this Venn diagram here to see, well, I've now defined the shape and the volume. Is there any connection between gases and liquids? There is a connection. So now what I do is I take my, and it won't erase now, okay? So I take my Erlenmeyer flask, I take the stopper out, I then fill it with a liquid. And when I fill it, I even want to fill it up more than what's in there, because then when I stick my stopper in, a little bit of water then kind of spits out, and you're like, doo-doo-doo. And with that, we can say, okay, now I have the same amount of gas, because gas is really tricky. It's going to fill every little smidgen of crack in space. By filling it up more, spilling a little bit out, we've now filled exactly the same amount of gas. And you're like, okay, now what? Well, we then take the liquid that's inside the Erlenmeyer flask, and we then put it in, and I'm going to try to draw it even just like some of the ones that we have here. We have our graduated cylinder here. And we pour our liquid inside there. And whatever it measures, whatever that reading would be on a graduated cylinder would be the volume of the liquid that was inside the container, which is also the volume of the gas that was inside the sealed container. So we're trying to use those connections of okay, I can't really measure the gas, but I can measure the volume of the liquid, which has a connection between the two, because both gases and liquids take the shape of their container. I can measure the volume of a liquid, but I can't of a gas. But if I seal the gas, now I've defined that this is how much gas would be inside there. It's the volume. Okay? Now, what we start to get into then is kind of the what's happening at the particulate level with these things. Why are they different? Okay? Why are they different? And it all comes down to energy. More specifically, kinetic energy. Some of you might have remembered that from 9th grade of what kinetic energy is, and that's the energy of motion. Okay? So you got to move to have your kinetic energy. The more kinetic energy that particle has, the more motion it has. The more motion it has, the higher the temperature can be measured. Because temperature is the average kinetic energy. It's a measurement of the average kinetic energy. Now, what a lot of people have a problem with is knowing that solids move, which just blows people's minds. They're like, what are you telling me? You're telling me a metal cylinder, or when my car, when it's parked outside, that the metal hood is moving? Yes, it is. Because if it has a measurable temperature, it's moving. The more that temperature goes up, the kinetic energy is now increasing. And what you're seeing with why is temperature a thing? Because it's the particles that keep hitting, smashing back into the thermometer. The more times that thermometer is getting hit, that energy is then able to be transferred into the usually it's now they're alcohol. It used to be mercury. Then we found out ingesting mercury isn't good when that broke off in your mouth. Okay. So it now gets transferred through the bulb, the glass bulb, to the little alcohol, and it goes up. It goes up because it's expanding, because it's getting all the energy that you have. Now, you get enough energy going, you smack these atoms around enough, they're going to break free from those bonds that keep them in their solid form, and then they melt, and they make a mess. You can think about just ice. You put ice in your hand, you're like, oh, but it feels cold. Yeah, it feels cold because it is cold. It has a low temperature. But your hand is going to give it energy. And it's going to start making a mess in your hand. It's going to go from a solid to a liquid. Phase transitions, changing the state in which it's found. Not going from like North Dakota to Minnesota, the state of matter. Okay? Not the state of mind or the state of being. It's two different things. If you sat there long enough with that water in your hand after the ice cube, eventually it would evaporate away, making it a gas. So the other phase transition. Now to get the last phase transition, from getting that gas into a plasma, takes a lot more of a kick in the pants. Because you have to excite the atoms a lot to get it to be a plasma. And water isn't going to do that. Okay? But it's all about the temperature.